We have seen what is vibration isolation and how it is measured using this transmissibility or isolation factor, and we will do a problem on this one. Here the problem what they have given is the mass of an electric motor is given. It's 120 kg and it runs at 1500 rpm. So this armature mass, its armature mass is 35 kg and its center of gravity lies 0.5 mm from the axis of rotation. So generally when you have this eccentricity 0.5 from its center of gravity of the motor, there would be some vibration disturbances will be there, and which will affect this performance of the motor. So the motor is mounted on 5 springs. So here the springs are used as a isolation material, and we use 5 springs with the negligible damping. Okay, we don't have damping, so that the force transmitted is 1/11th of the impressed force. So here the force transmitted to the impressed force or the applied force is nothing but your transmissibility. So that is what they have given. So force transmitted Ft is equal to 1/11th of F. Assume that the mass of the motor is equally distributed among the 5 springs. We have to determine stiffness of each spring, dynamic force transmitted to the base at the operating speed, and the natural frequency of the system. So these 3 are the things which we need to find. Yes, coming to the mass given, the mass of the motor is kept as M1 120 kg, and the armature coil is M2 is 35 kg, and it has some deflection, or the axis have the eccentricity 0.5 mm. So 5 into 10 power minus 4 meter, everything we are converting into SI units, and as we said the transmissibility is equal to 1/11, and the speed 1500 rpm. So from which we can calculate omega, that is this angular frequency or angular speed, thus 2 pi n by 60, and which gives you 157.1 radian per second. This 157.1 radian per second is external frequency, right? And we know that since we were given the transmissibility ratio, here the transmissibility ratio epsilon is equal to 1 by omega n the whole square minus 1. See here, why we are taking this formula? Because we don't have the damping factor. So that is what we have seen here. So suppose if it is greater than, the ratio is greater than 1, we can adopt the second one, the first one or the second one. Here let us consider the second one, so that we have found out what is omega, that is 157.17 whole square. So cross multiplying and taking LCM. So the only unknown thing here is omega n square. So you just cross multiply it. So what happens? 11 omega n square is equal to 157.1 whole square minus. So from which we can calculate what is omega n, that is 45.35 radian per second. So once you find out the natural frequency, natural angular frequency or circular frequency, you can find out the stiffness, because already the mass of the motor is given, because omega n is equal to root of S by m. Here we are taking m1. So you substitute, therefore the squaring on both sides will get omega n square equal to S by m1, or S is equal to m1 into omega n whole square. So this m1 is 120 kg mass of the motor, and omega n what we have found out is 45.35. After squaring it 2057, so you will get 246840 Newton per meter. So this is the net stiffness. So we are using 5 springs, therefore each spring will have, when you divide this answer by 5, we will have 49,368 Newton per meter. This is the stiffness value of each spring. And now second one, what is the was dynamic force transmitted to the base. So the dynamic force transmitted. So first we have to find out what is the applied force. So applied force F is equal to the mass of the armature into its angular speed of the motor into the eccentricity or the radius at which it is lying. So you can substitute all these value and you will get 432 Newton, and we already know the transmissibility ratio is equal to 1/11. So transmissibility ratio epsilon is equal to Ft by T, therefore Ft is equal to epsilon into F. So this epsilon is 1/11 and F what we have calculated is 432. So you can find out 39.27 Newton. And the third one is natural frequency. The natural frequency is the first thing we have found out here, 45.35 radian per second.